Welcome to your first lecture video of the semester for Gen Chem 2. We're going to be talking about Chapter 13, which is all about properties of solutions. Okay, the way this is going to work is I'm going to deliver this lecture very much like I would deliver an in-person lecture, standing at the whiteboard. The only real difference is I don't get any interaction from you folks that makes things lively, and you'll get a little bit less of my bad jokes, and I seem like a disembodied voice. But hopefully these lectures will be useful to you, and feel free to pause, rewind, and replay these lectures at your discretion. So, talking about solutions, and one of the first things that we need to understand is that there is a natural tendency to mix. You'll have to forgive my spelling and my handwriting. I'm a scientist, not an English major. But there's a natural tendency to mix, which is generally a spontaneous thing. You'll also have to forgive me, I'm left-handed, so I often bump things on my screen from time to time. This is generally a spontaneous thing. Okay. And we want to ask the question, why is it spontaneous? Because it leads to an increase in entropy. Okay. So increasing entropy is the way the universe wants to operate. The universe wants more ways to be, more ways to be. I'm going to put ways in quotation marks, and I'll explain that here in a second. Wants more ways to be. Okay, and what that means is that entropy is, it's all about what we call microstates. And a microstate is an option for movement, direction, expansion, contraction. It's a way to be. So if we can increase the options for movement or direction for particles or molecules, we're increasing entropy. So let me just write all that stuff out here for you. Microstates. Okay. And microstates, like I said, they are options for movement or direction. So imagine, if you will, a particle moving in a straight line left to right at a constant speed. If I suddenly give that molecule the option to go up or down, in addition to left to right, now I've increased its microstates and increased the entropy. So if I imagine a beaker of water, you have to forgive my drawings. All right, and let's say that each one of the little red circles is a water molecule. And these water molecules are moving around, they're bumping into the sides of the container. It's still a liquid state, so they're still sort of stuck together. They're still touching each other, but they're able to slide past each other. So there's certain things that these water molecules can do. Now, if I introduce some other thing, let's say I dissolve some sodium chloride in my water, now I've got all these particles of something else. Now I have not only water molecules bumping into each other in the walls, but now they're bumping into solute molecules, the sodium chloride molecules. Those sodium chloride molecules are now bumping into the walls, bumping into the water molecules, bumping into other sodium chlorides. Now I have more things happening inside my beaker, and hence I have more microstates and more entropy. So the mixing of those two things increases the entropy. That's why that mixing tends to be generally spontaneous. The universe wants more entropy. Okay? So there are three factors that influence solution formation. Okay? Solution formation. And remembering from Gen Chem 1 that a solution is made up of solute and solvent. The solute is the minority part, the solvent is the majority part. But the formation of a solution is governed by, let's talk about the first one, our solute-solute interactions. Okay, and what that means is that in order to make a solution, we have to overcome these to disperse solute particles. Okay, meaning that the solute particles themselves are stuck together before they're mixed with the solution. So in order to make a solution, the solute particles have to be able to come apart from each other in order to disperse throughout the solvent. Okay, so we have to overcome solute-solute interactions in order to make a solution. So our second factor that influences solution formation are solvent-solvent interactions. Okay, and what that means is that in order to let mixing happen, our solvent molecules have to make room for the solute particles to come in and interact. So we have to overcome these interactions to make room for solute particles. To make room solute particles. Okay. So our third factor, and you may have guessed what it might be, are the solute-solvent interactions. Okay, and what these are is what happens at the time of mixing. Okay, so we've overcome our solute-solute interactions, so our particles of the solute have come apart. We've overcome our solvent-solute interactions. We've overcome our solvent-solvent interactions, so we've made room for the solute particles. Now we have to think about how the solute and the solvent interact with each other. So now that we've overcome the first two, now we're actually mixing and we have some interactions. Right? So solution formation can be endothermic or exothermic. Okay? And just to refresh your memory, endothermic means that energy is going in. Exothermic means that energy is coming out. So either we're absorbing heat from the surroundings or releasing heat to the surroundings. So we can have solute-solute interactions. And we can talk about those in terms of enthalpy of the solute, delta H of the solute. Our solvent-solvent interactions, we can talk about those in terms of the enthalpy of the solvent. And our solute-solvent interactions, talk about the enthalpy. That should be a delta. That's a triangle. Mixing. Okay. So remembering Hess's law, so we can add the delta H's to get the delta H for the process. Add the delta H for each step. Get the delta H for the process. Okay. So in sort of mathematical terminology, we can symbolize this saying delta H for the solute interactions plus the delta H for the solvent interactions plus the delta H of the solute-solvent interaction, so delta H mix, gives us our delta H for the solution. Okay. So to look at an example here, so if I add some magnesium sulfate, salt, to water, the delta H of solution is negative 91.2 kilojoules per mole. Okay, so remembering the signs for enthalpy, so a negative sign means that this is exothermic. Gives off heat. Okay. So a negative sign, just as a reminder, so I always teach that the signs on things like enthalpy are much like the signs on transactions in your bank account. So if you're looking at your bank statement and there's a negative sign in front of a dollar amount, that means that money came out of your bank account. So much like that with energy, talking about enthalpy, if there's a negative sign in front of the value for the enthalpy, that means that energy has come out, so it's releasing heat. Okay. If we add some ammonium nitrate, on the other hand, to water, the delta H of solution is 26.4 kilojoules per mole. Okay. The sign on the enthalpy is positive, so it's endothermic. Much like a positive symbol in your bank statement, money is going into your account, so energy is going in. So endothermic means it absorbs heat, or feels cold. Okay? So much like a chemical cold pack. All right. So our next topic that I want to talk about is dealing with things dissolving. Okay, so talked about making mixtures, making solutions. Now we need to talk about how and why things do that. And it has to do with solubility. Now, in the previous semester, you learned about solubility in terms of what things will dissolve and what things won't dissolve, what things are soluble or insoluble. But now we're going to get into a bit more of the nitty-gritties of the details. Why and how much, and being able to calculate that sort of thing. So as a solid dissolves, more solute particles are present. More solute particles are present in the solution phase, which increases the likelihood of collisions. Okay? And when we have collisions of solute particles, what we get is a process called crystallization. Okay? So crystallization is the opposite of dissolving. Okay? And believe it or not, you already know a little bit about this. So if you've ever had the experience of making rock candy or putting too much sugar in your tea or anything like that, there's a certain point where no more material will dissolve, and instead it starts to make solid again. Okay, so thinking about what a equation might look like for this process, if we have solute plus solvent is going to be in equilibrium with solution. Okay, going forward, going left to right, that's dissolving. And going from solution to separate solute and solvent, that's crystallization. Okay, so dissolving into solution, coming out of solution to making separate solute and solvent is crystallization. Okay. So our forward process is dissolving, and the reverse process is crystallization. Okay, or undissolving. Now here's the kicker. So that double-headed arrow, I used the word equilibrium. Okay, so when both processes are equal, we have what's called a dynamic equilibrium. Dynamic equilibrium. Okay, meaning that both processes are happening at the same time. Okay, at dynamic equilibrium, no more solid will dissolve. Okay, once you've reached equilibrium, as much as will dissolve is going to, because if you add any more, you're going to start getting full recrystallization. Okay, so forward processes and reverse processes are equal, so no more is going to come apart. Okay? So we're in this sort of building process. So now that we understand that concept, the idea that the amount of solute that can dissolve in a given quantity is called its solubility. Okay, so key point here. I'm going to give this a gold star. The amount of solute that can dissolve in a given quantity of solvent okay. Now, solubility is affected by temperature. Okay. If you've ever tried to, in your kitchen, make rock candy or what we refer to as simple syrup, you understand that if you heat up the water, so it's easier to get more sugar to dissolve in boiling water than it is to get sugar to dissolve in room temperature water. Okay, so increasing temperature increases solubility of solids. Okay, that's actually a really important topic, but we're not going to get into it just yet. But understanding that heating things up will allow us to dissolve more solid in a solvent. Okay. Gases, on the other hand, go exactly the opposite. If you cool things down, you can get more gas to dissolve in water. But we'll talk about that in a little bit. Okay. So, for example, let's talk about solubility of sodium chloride. Okay. For example, solubility of sodium chloride in water at 0 degrees Celsius is 35.7 grams per 100 milliliters of water. Okay. That means that we can get as much as 35.7 grams of sodium chloride to completely dissolve in just 100 milliliters of water. That's not very much water, and it's actually quite a bit of salt. Okay. Now, if only 10 grams are dissolved, we say that the solution is unsaturated. Okay? Meaning that we can still get more in there. We can still dissolve more. So if the solubility of sodium chloride is 35.7 grams per 100 mils, if I've only got 10 grams in there, I can still dissolve more until I get to the saturated point. Okay, to the point where no more will dissolve till I reach that dynamic equilibrium. Okay. Okay. So now the question becomes, so you've already learned about the topics of things, will things dissolve, won't things dissolve. So let's talk about that. So will something dissolve? So and that is determined by the solute-solvent interactions. Those determine will it dissolve. Okay. So we're going to return to the concept of intermolecular forces. So if the intermolecular forces match, then yes, it will dissolve. Not question mark, it should be an exclamation point. Okay, so remember the concept of like dissolves like. So if we look at our list of intermolecular forces, remember what those are. So we have London dispersion, or sometimes just referred to as dispersion. We have dipole-dipole interactions, so polar things. We have hydrogen bonding. So things that have a hydrogen bonded directly to an oxygen, nitrogen, or fluorine. And we also have ion dipole interactions. Okay, so the whole concept with this is that the stronger the interactions, there should be an S there, stronger the interactions equals greater solubility. Okay, so if we have very strong London dispersion interactions versus weak London dispersion interactions, we'll have greater or lesser solubility. If we have strong interactions with some very, very polar molecules, so strong dipole-dipole interactions, we'll have greater solubility, etc., etc. Okay, so polar, so the idea of like dissolves like, right? So if we have polar things with polar things, if we have non-polar with non-polar, right? So if those situations happen, we can mix, right? But remembering that polar with non-polar, no mixing. Okay, we call these situations immiscible. Immiscible. Okay, mixing, we say that things are miscible. Okay, or they mix. Okay, if they don't mix, we say immiscible. Right, so let's take a look at how various types of molecules, what their solubility is in water. All right, so first up, we're going to look at, let's say, hexane. Hex meaning 7, ane meaning that all of the carbons are singly bonded. So we have 1, 2, 3, 4, 5, 6, 7. Right, and imagine each one of these lines is connected to a hydrogen atom. And I'm not going to draw all of them because that's very, very tedious. Okay, so think to yourself, what type of interactions is this molecule capable of? It's non-polar. There are no oxygens, nitrogens, or fluorines, so there's no possibility of hydrogen bonding. There's no dipole to interact with an ion, so the only thing that this thing is capable of is dispersion forces. Okay, water is a polar molecule, so we have a non-polar with polar. The solubility of hexane in water is a simple 9.5 milligrams per liter. Okay, so let's look at the next one. So the next one would be benzene. Very common molecule in organic chemistry, and it is a cyclohexane ring. 3 of the bonds are doubles, and we have a hydrogen sticking off here at each corner. And each corner of that hexagonal ring is a carbon. Okay? So again, nonpolar molecule, no hydrogen bonding. Being nonpolar, it doesn't have a dipole to interact with ions, so no dipole-dipole. Again, all we have is dispersion forces. But being of a slightly different shape, different molar mass, we have a little bit different, about twice the solubility in water that in hexane does. We can get 1.79 milligrams of benzene to dissolve in a liter of water. All right, let's go even simpler. Okay, so our next one is carbon tetrachloride. And being as this is our first lecture, and some of you are coming from a different school, I hope that when I'm using some of this terminology, some of this nomenclature, your knowledge base is pinging, saying, oh, I know what that means. Carbon tetrachloride, meaning there's 4 chlorines attached to a carbon. So nomenclature is important to me, and I will be occasionally making you use your nomenclature knowledge throughout this term. Okay, so let's think. So everything has dispersion forces. Great, fine. This thing is small. It's relatively round. It's tetrahedral in molecular geometry. So even though we have polar bonds between the carbon and the chlorine, the tetrahedral shape of this molecule, all of those polar bonds are counteracting each other in all 4 directions. So this is a non-polar molecule. We have no hydrogen bonding. It's non-polar, so no ion-dipole interactions. This thing has a terrible solubility in water of 0.79 milligrams per liter. Okay, so our last example, let's take a look at what happens when we change up our structure just a little bit with acetone. Okay, the structure for acetone looks like this. So we have carbon double bonded to an oxygen and bonded to 2 CH3 groups. Okay. So the CH3 groups down at the bottom are nonpolar, okay? But I have a nice strong pull up towards that oxygen. Okay, even though this thing is trigonal planar, I don't have an equal pulling of electrons in this molecule, so we are polar. Okay? In general, we have a dipole that's pulling up this direction. Okay? So it's a polar molecule, and just by that nature, right, if I put this polar molecule in water, I go from, our previous example had 0.79 milligrams per liter. Not even a whole milligram will dissolve in water, okay, in a liter of water. When I do this with a polar molecule like acetone, I can get 1 whole gram. 1 whole gram in a liter of water. Okay, so this concept of like dissolves like is really important, right? If I try to put non-polar things in a polar solvent, I'm not going to be able to get very much to dissolve, right? But if I go polar with polar, suddenly plenty will mix. So our next topic is talking about how gases dissolve in water, okay? Okay? If you've ever dealt with anything involving aquatic life or environmental work of any kind up until this point, you have some concept of a thing called dissolved oxygen. And in fact, that is what fish and other gill-breathing animals use in order to breathe underwater. The gills extract the oxygen that's dissolved in the water, right? So dissolving gases in solvents is a thing, and it's important for us to study. And what's important to know about this is that the concentration of the gas, so C of the gas, all right, and let's make sure we know this is concentration of the gas, okay, is directly proportional to the pressure of the gas. Above the solvent. Okay, so we have a thing called Henry's law, which allows us to calculate this sort of thing. Henry's law. Okay, and Henry's law looks like this. The concentration of the gas in the liquid or in the solvent equals K gas, which is a constant, the Henry's law constant for that particular gas, times the pressure of the gas above the solution. Okay, so let's annotate this just a little bit so that we're really clear. So this is concentration of the gas dissolved in the solvent. Okay. This one right here is the Henry's law constant. For the particular gas. And this one over here is the pressure of the gas above the solvent. Sometimes I like to think about this as like squeezing gas into the solvent. So if you have a greater pressure above, you're pressing down on the surface of the solvent with this gas, you're going to be able to get more of the gas to dissolve into the liquid or into the solvent. Okay? So how are we going to use this? Let's talk about that a little bit. So when we do Henry's law problems, we need to know what the Henry's law constant is. Okay, in order to understand either what is the pressure above the solvent or how much gas is dissolved, we need to know K gas. So when doing Henry's law problems, step one is to find K gas at a given temperature and solvent. Okay? And we do this from known values. So known solubility and known pressure of gas. Okay, so rearranging Henry's law, we can solve for K gas equals C gas over P gas. Okay, and this is for known parameters. Okay, so a lot of work has gone into making tables of these types of things. So given a certain temperature and a certain solvent, we know that a certain amount of a gas will dissolve. We know the solubility of a gas in a particular situation. Okay, so we're going to use that information to find K gas. Now the next thing to do, once we know K gas, we can use it to find the pressure of the gas for a desired concentration. or C gas. Okay, so let's do an example problem. I know I've said let's do an example, and I really just gave you information. This time we're going to do an actual problem. So let's find, so step one, let me change colors here, let's do green. Step one, let's find the Henry's law constant for oxygen at 20 degrees in water at atmospheric pressure. Okay. Find KO2 at 20 degrees Celsius from known information. Okay, so we go to a table and we find that solubility of O2 in water at 20 degrees Celsius is 48.9 milliliters of O2 per liter of H2O. And that's per 1 liter. Okay, so atmospheric pressure is just 1 atm. Okay, so the pressure of the oxygen on the surface of some water is 1 atmosphere of O2. Okay, so K gas, or KO2, is our, coming back up here, K gas is C gas over P gas. So I use this known information, 48.9 milliliters of O2 per 1 liter of H2O divided by 1 atmosphere of O2 gives us our Henry's law constant of 48.9 milliliters O2 per liter H2O times atmospheres of O2. Okay, pretty straightforward, that bit of a problem. So let's use it in a more complex situation. So our next thing that we want to do is find the pressure of O2 needed to maintain a given concentration in water. Find the pressure O2 needed to maintain a concentration of 2 parts per million. Okay, so 2 parts per million is basically, the reason I picked that number is because it's sort of the minimum amount of dissolved oxygen needed to maintain aquatic life. Okay, so imagine you have a pond or a small lake or something, and you've got fish and plants and things in there. Those fish and plants need a bare minimum concentration of O2 dissolved in the water of 2 ppm. Okay, and parts per million is the same thing as saying grams per million grams. Okay, so we have a little bit of a difficulty here in that our K for O2 is in milliliters and liters. Okay, so milliliters per liter to be exact. So we need to convert our ppm to milliliters and liters, okay, before we can do our Henry's law equation. So the next steps, I'm going to show the conversion of ppm to milliliters per liter. Okay, because we need our units to match our units of K. Okay, so we have 2 ppm is the same thing as saying 2.0 grams of O2 per million grams of H2O. okay? Grams per million grams, right? So let's convert to moles, because that's always a good step. Moles of O2 is roughly 32 grams. Okay, and at standard temperature and pressure, 1 mole of gas occupies 22.4 liters. Okay, now I want to convert that to milliliters and get rid of the liters of O2 on top. Okay, so we've got 1,000 milliliters of O2 per liter of O2. Okay, so if I stopped here, I would have milliliters of O2 per million grams of water. Okay, so if I go through these steps, at this point I have 1,400 milliliters of O2 per million grams of water. Okay, so let's do a little conversion. Let's get from the million grams of water into liters. Okay, so this is the same thing as saying 1 million grams of water also equals 1,000 liters. Okay, because of the solubility, not the solubility, but the density of water. So this also equals 1,400 milliliters of O2 per 1,000 liters of H2O. All right, so we do a little canceling out, and what we end up with is 1.4 milliliters of O2 per liter of H2O. Okay, so this is now our concentration of O2. Okay, that we want to figure out what pressure do we need in order to maintain that minimum concentration. So our minimum pressure of O2 equals the concentration of O2 over the K for O2. Right? So we have 1.4 milliliters of O2 per liter of H2O divided by our Henry's Law constant, which was 48.9 milliliters of O2 per liter of H2O times atmospheres of O2. And we find out that all of our units, our milliliters of O2 cancel out, our liters of H2O cancel out, leaving us with atmospheres of O2 on the bottom of the bottom, which makes it the top. So 1.4 divided by 48.9, I love doing that to students. It's on the bottom of the bottom, which makes it the top. It's all about dividing fractions, folks. All right, but what we find out is that in the end, we need a minimum pressure of O2 of 0.0286 atmospheres. Okay, and that's what we needed to maintain 2.0 ppm. Okay, so lucky for us, the actual pressure is somewhere around 0.21 atmospheres. Okay, so we have 10 times more the pressure than we need in order to maintain that minimum concentration. Okay, so our aquatic life lives, which is always nice. All right, our next topic, I'm going to move to a fresh page. So we've been talking about mixing gases with liquids. So our next topic is dealing with liquid and liquid mixtures. Liquid mixtures. And for this, we have a thing called Raoult's law of vapor pressures. Raoult. Okay. And Raoult's law looks like this. So the pressure of gas A, the vapor pressure of gas A, is equal to the mole fraction of A in the solution times the partial pressure of pure A, so P0 of A, at a given temperature. And so let's annotate that so it's clear. So this is the vapor pressure of A. Okay. This is the mole fraction of A in the solution. Okay. So we're talking about in the liquid solution, how much of compound A do we have? Okay. And then this P0 of A, this is the pressure of A of pure A. Okay, at a given temperature. Okay, so just as a reminder, what are we talking about when we're talking about vapor pressure? So we'll come back to our beaker. All right, let's imagine that we have some liquid, and we'll call this compound A. Okay, so liquid of compound A. Okay, at the surface of every liquid, some of compound A can become a gas. Okay, and that gas sits right at the surface of the liquid and exerts a pressure on the surface of the liquid. Okay, so that is the vapor pressure of compound A. Right, now imagine that I have some of compound B in the liquid mixture. Okay, that means that I also have some B in the vapor above the liquid. Okay, so the amount of A that's in the liquid mixture is proportional to the amount of A that's in the vapor. Same thing with the amount of B. Okay, so this is how we're going to use Raoult's law in order to determine things. Okay, so the amount of the mole fraction of A, as the amount of A in the solution, in the liquid, goes down, the amount of A in the vapor also goes down. Okay, so this is kind of an important topic. So let's do a little star of this. So as the mole fraction of A goes down, the vapor pressure of A above the solution also goes down. Okay, so if I have less A in the mixture, I have less A in the vapor mixture. Okay, so what is that? How does that affect anything? This is also an important thing. So A will boil when the vapor pressure of A equals the atmospheric pressure. Okay, so if I have less A, then it takes me longer to get to the equal atmospheric pressure. Okay, so what this means is that if A boils when the vapor pressure equals the atmospheric pressure, then as A goes down, as the mole fraction of A goes down, it forces the boiling point higher. As the mole fraction of A goes down, the boiling point goes up. Okay, so to try and clear this up, and because I feel like I'm using a lot of words here. So most of the time your vapor pressure above the liquid is fairly low compared to atmospheric pressure. Okay, so in order for something to boil, we need to make more vapor above the solution. Okay, so we need to increase the vapor pressure. We need to increase the amount of vapor above the liquid. Okay, once we get enough vapor above the liquid that pressure equals atmospheric, the liquid will boil. Okay, so but if I have less of A in the mixture, okay, that means that I have less of A above the liquid in the vapor. And I have to put more energy in order to create more vapor of A so that it equals atmospheric. Okay, so if I have a lower mole fraction of A in the liquid, that forces the boiling point higher. Tricky, right? So let's do a little bit of practice with Raoult's law. Okay, so for example, if I have a mixture, a liquid mixture of hexane and pentane. Okay, two nonpolar molecules. All they have is dispersion forces. So this is what we refer to as an ideal mixture, because it's completely miscible. Mixes perfectly. Okay, so nearly identical intermolecular forces, so it mixes really, really well. Okay, so if the mole fraction of hexane is 0.25, so roughly 1/4 of the mixture is hexane, and the vapor pressure of pure hexane, so the P0 of hexane, is 149.1 milliliters of mercury, then the amount of hexane in the vapor vapor pressure of the hexane alone is just the mole fraction times the pure hexane. So the vapor pressure of hexane in the mixture above is 37 millimeters of mercury. Okay. So conversely, if we had the information about the pure pentane, so if we know the P0 for pentane, we can say the vapor pressure of the pentane of the mixture, 0.750 times its P0 is 508.5 millimeters of mercury. It's 381. Okay. So if I want to know what is the vapor pressure of the mixture, of the total, so the total vapor pressure, or we can say P of the mixture, (37 plus 381) is 418 millimeters of mercury. Whoops. Okay. So halfway to boiling, just all by itself. And remembering Dalton's law of partial pressures, that the pressure total is the sum of the partial pressures. Okay, so Raoult's law is pretty straightforward. The P0s, P0 of a gas, these are tabulated values. You will never have to memorize these. You won't have to be expected to know them. You may be expected to calculate one, but you'll be given sufficient information to do so. Right? But P0s, that pressure of the vapor pressure of the pure gas, the pure component, those are tabulated values that you will either look up or be given something of that nature. Right?